Hi, everybody. Welcome to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. I haven't given a plug for my book yet. It's actually a three-volume series. It's available on Amazon.com in both Kindle and paperback format. I forget the price, but you can purchase any one of these volumes or any combination of these three volumes or the whole set if you want. And I think it's a good buy. And I'm almost done with volume one of this video series. You can just watch the videos if you don't want to pay the money. Um, but I'm kind of wrapping up chapter eight, which is on computation. Probably only another week or two to go in this chapter. But now I'm starting a new section, section 8.5, which is on computational complexity. And there's kind of two aspects of computational complexity, running time and memory. So whenever you write a computer program, you always have to worry about how long it takes to run and also how much memory it uses. Those are kind of practical considerations. So anyway, let's begin. So yeah, I just kind of went over what computational complexity is. And, usually when you have an algorithm, I'm going to give you some examples. Maybe it's good to just jump into examples. So, yeah, let's first start talking about running time. That's usually the thing that, computer scientists seem to be most interested in. Because nowadays, especially nowadays, when computers are very fast, and not only that, but they have a lot of memory, and memory isn't as big an issue as it used to be. Still an issue, but anyway, just for an example, what if we were adding two numbers, two non-negative integers to make it specifics? Let's call it little m and little n. Well, if we use the normal way that you learned how to add when you were in grade school, you write down the numbers in base 10, and then you add each column, which corresponds to each digit of each number. And um, let's say, so if your numbers are m and n, then the number of digits is approximately the base 10 logarithm of the number. So, for instance, if your number was 1,000, it would have four digits, but you can round that down to three, which is the base 10 logarithm of 1,000. If it was 999, it would have three digits. It's actually the ceiling of the base 10 logarithm. Yeah, that's specific. That's an exact formula. So the number of decimal digits of any positive integer is equal to the ceiling of its base 10 logarithm. Um, but computers don't work in decimal, they work in binary. So if you're adding two numbers on a computer, it first converts them to binary. I'm not going to worry about the computational complexity of doing that. That's very fast, by the way. That's kind of built-in code into the computer that's kind of going on behind the scenes. But anyway, just like in decimal, the number of digits of a base 10 number is the ceiling of the base 10 logarithm. In binary, it's the ceiling of the base 2 logarithm. So if we were adding the numbers, say m and n, where m has, then the number of digits of m is the ceiling of the base 2 logarithm of m, and the number of digits of n is the ceiling of the base 2 logarithm of n. So, the computational complexity is just kind of equal to the sum of those two things. And I'm calling that k here, k for computational complexity. That's kind of the number of bits of information that are given into the computer. So this is right now. This doesn't have anything to do with running time. Now we're just talking about the complexity of the input that we're given the computer. So we give it two numbers, which I'm calling m and n, and computational complexity is defined as the number of bits of information in the input, and that's just equal to the ceiling of log 2m plus the ceiling of log 2n. We can call that k if you like. And now, what about the running time? How fast would it take for the computer to add these two numbers? Well, it adds them column by column. It's just adding bits in each column. That's a very simple thing to do. That's really just one operation for each column. Um, um, and yeah, I wrote it as 2K here. I'm not sure why I wrote it as 2K, but yeah, well, it's reading 2 bits. That's right. So I guess the computational complexity of a single binary addition is 2, because you could have an overflow too, right? I mean, if you're adding, there's sort of 4 possibilities of adding 2 bits: 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. That's 2 bits of information. The result can be a number up to um, 2, I guess, in this case, but you require 2 bits to write it down. So 2 bits per column, and then we have when you take the maximum of the way I did it here, I'm just taking a k, the log 2m plus log 2n. I think it's really the max of log 2n on log 2n. But oh yeah, I'm coming up with an upper bound. So really, if m is the bigger number, then it's really just 2 times the ceiling of log 2m. But in general, we don't know, ahead of time which number is bigger, so we can put an upper bound on this limit. It's just, it's certainly less than or equal to the sum. Max of 2 numbers is always less than equal to their sum. I think I should have switched to the next slide. Yeah, because here's what I do the calculation. Um, so remember, I was calling k the ceiling of log 2m plus the ceiling of log 2n, and then that's certainly twice that number is an upper bound for the running time of this algorithm. So the running time is less than or equal to 2k. Um, it's basically a constant times k times the number of bits of your so this is what's called linear running time. I'm going to get to this later. A couple of lessons I'll go over big O notation. That's really what we care about here. But the point is, when you're doing addition, the running time is proportional to the complexity of the data you're giving in bits. So that's running time. With a simple example, addition. Um, what about memory? Um, similarly, memory is also less or equal to 2k, because the amount of memory in your computer, it has to, not only does the computer have to store all the input into its memory, so the memory allocation of any program is always at least as big as the size of the input. It might be bigger, because you have to store more numbers when you're doing your calculations. In the case of bitwise addition, you have to store the numbers that you're carrying. So, you have kind of an additional carry bit for each column. That's another K. So, anyway, the total is going to be, the upper bound is going to be 2K again. Again, it's linear in the size of the input. So addition is very simple. Addition is just linear. It's if you like, people usually write it O of N. I'll get into that later when I go to you know anyway, let's just do another example. So we just looked at addition. Addition is pretty simple. What about multiplication? And I'm sure you guys in grade school, when you were learning how to multiply on paper, pencil and paper, you learned shift and add multiplication. And so how many operations involve in shift and add multiplication? Suppose that, again, we're given 2 numbers, m and n, and we want to multiply them. So we have to look at the complexity of our data. And like I said earlier, the number of bits of m is a ceiling. I'm calling that k here, which is the ceiling of the base 2 logarithm of m. And I'm calling L the ceiling of the base 2 logarithm of n. And if you remember, when you do shift and add multiplication, you have to look at each place, each decimal digit of the second number you're multiplying by, and then you have to use all the base 10 digits of the first number for each of those. So you're actually multiplying them together. The total number of operations you do for shift and add multiplication is equal to k times L. It's if you're doing it in a decimal, it's the product of the base 10 logarithm of the first number and the base 10 logarithm of the second number. So it's k times L. And remember, k was a complexity of the first number, and L is a complexity of the second number. Uh, in the worst case, when they have both the same number of digits, say the M and M are the same size, then L would be equal to K, and the running time would be proportional to K squared. So this is a case. This is shift and add multiplication is a lot slower than addition, even for a computer. It turns out there are more efficient ways to multiply than shift and add. There's something called the fast Fourier transform, which is a lot faster than shift and add. But shift and add is what's called an O of n squared algorithm. If your complexity of your input is n, in this case k, then the running time is going to be proportional to k squared. This is in sharp contrast with addition, where the running time is just proportional to k. So running time is a linear. I mean, addition has a linear running time, and the shift and add multiplication has quadratic running time. The memory, however, is still linear for shift and add because all you have to do, the only extra bits of information you have to add. Uh, is that right? Actually, I think they're both. I mean, you could do the additions one step at a time. I think there are more efficient ways in terms of memory to do shift and add multiplication. You could, I mean, the most primitive way to do it is you can store all the carries for everything you're writing down in memory, and then you're going to get k squared of those. But you don't really have to store them. You can do the addition one step at a time at the end. Remember, you're writing down all the columns, and then you're adding all the columns. Well, actually, yeah, when you're writing down all the columns, that has to be in the memory. So yeah, I guess both memory and running time are k times L in this case, or if they're both the same size, k squared. So, but for both running time and memory, the complexity is or k squared. It's quadratic. Um, anyway, so that completes my video for today on computational complexity. Next time I'm going to talk about big O notation. Anyway, that completes my video for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.